Having done several advanced playlists in mathematics, I feel the time has come for me to start revisiting some foundational mathematical stuff because you need to know the basics before going to more advanced things like calculus and everything. So, and that's why in this video, I'll be starting a new playlist on polynomial equations. And in this very first video, we'll look at fundamentals of polynomials, specifically definition and structure of polynomials. So what are polynomials and things like that? That is what we are considering here. Okay. So first we go for the the basic definition of polynomials and the big picture. First of all, we need to understand that okay, well, I like to break words down as much as possible, you know. So when you hear the word poly, you have polynomial, okay? Poly, of course, means many, okay? Poly means many, and nomial means terms. So it means that we are looking at a situation where we have expressions involving many terms, right? So, with that taken care of, so let's go back and look at some how we can build up things until we get to the idea of polynomial. So, a polynomial in one variable x is a special kind of algebraic expression built from a variable x, number one. Then we have real number coefficients, no complex number coefficients, and all that. Then non-negative integer exponents of x. That means x has powers, but they are non-negative and they're not even fractions. Then you have combined. They are also combined using only addition, subtraction, and multiplication, right? So it means that okay, you're going to see all of this. So I think let me just go with the flow. So general form, for instance, you have an x raised power n plus an minus 1 x raised power n minus 1 plus everything up to a2 x to x squared plus a1 x raised power 1. That's just x, right? Then a naught x raised power 0, which is simply a naught, right? Because x raised power 0 is 1. Where a naught, A1, AN are real numbers. These have got to all be real numbers. They cannot be complex numbers, you know. So once they become complex, then you're no longer talking about polynomials. Another thing that makes a polynomial is that n is a non-negative integer. So all these powers you have here, they are non-negative. So they can be -2, -3, or fractions even. So each exponent is a whole number, okay? So the coefficients are real numbers. The powers are non-negative integers, and each exponent, each of the powers n is a whole number. The least it can be is 0, then the next is 1, 2, and so on and so forth. It can't go negative, and it can't go non-whole numbers. You can't have like x raised power 1 over 2, x raised power 3 over 2. In that case, it will no longer be a polynomial. Okay. Now, let's talk about algebraic expressions, terms, and coefficients. So these are like building blocks of polynomials. So when we talk about algebraic expressions, right? By the way, when you hear algebra, it's basically representing reality with letters, with figures. Okay, let me even get a vivid definition of algebra. Let's get that from AI, right? From, of course, these days, if you Google something, Google gives you the AI thing. Okay, here it just says algebra is a branch of mathematics that deals with abstract systems known as algebraic structures and the manipulation of expression within those systems. But I think one basic definition of algebra I've always known is that you represent realities with symbols, something like that. Okay, so an algebraic expression is any combination of variables. So you have variables, constants, and operations. So the variables can be x, y, and t. The constants can be any whole number, any number, whether whole or not, right? You talk about variables, talk about constants like 2 minus 7 half. You have operations like plus, minus, multiplication, division, powers, roots, and so on. Example, 3x raised to power 4 minus 2x plus 7 is an expression. Don't forget, our playlist is about polynomial equations. So this is simply an expression. This becomes an equation if once you say 3x raised to the power 4 minus 2x plus 7 equals 0 or equals anything else, maybe equals 2x plus 5 or equals 7 or equals, once you equate it to something, then it becomes an equation. But alone, it is just an algebraic expression. So equate it to something, then it becomes algebraic equation, right? So it means you need to get a polynomial which equates to something for you to now have a polynomial equation. So that's talking about algebraic expressions. So let's talk about terms now. So in this algebraic expression, 3x raised to power 4 minus 2x plus 7. So a term is a single piece separated by plus or minus. So you see 3x raised to power 4 is separated by minus, and you have 2x, which is separated from 7 by plus, right? So in 3x raised to power 4 minus 2x plus 7, the terms will be each term separated by sign. So you have 3x raised to power 4, okay? Then minus 2x, you take it together with the sign, then plus 7. 7 or plus 7 is the same. So these are the terms of that algebraic expression. So that's the idea of terms. Then when we talk about coefficients, the coefficient of a term is the numerical factor multiplying the variable part. So you see 3x raised to power 4. 3x raised to power 4 minus 2x plus 7 is more or less like, 3x raised to power 4 is it minus 2x now? Minus 2x plus 7 is more or less like 3 times x raised to power 4. Okay, minus 2 times x plus 7 times 1, if you like. Okay, that's basically what that looks like. Okay, so for coefficients now, the coefficient of a term is the numerical factor multiplying the variable part. So the variable parts here will be x raised to power 4, x, and x raised to power 0. The invisible x you have is x raised to power 0. So the coefficients in this case would, so in 3x raised to power 4, the coefficient is 3. And for minus 2x, the coefficient is minus 2. And for the constant 7, that can be seen as 7x raised to power 0, like I just said. So the coefficient in this case is 7. Okay. So now for algebraic expressions, you can now tell apart the variable. Of course, the variable here is just x. So it is a single variable in this case. And then the coefficient are the numbers in front of them. And terms are each part, if you take them one by one, you have the terms. Then let's talk about a formal definition of a polynomial in one variable. So when we say one variable, it means that we don't have it like maybe x plus y minus 7x minus 3y, equals something, or just that. So formal definition of a polynomial in one variable, that means we're just talking about either just x or only y or only p or only q or whatever variable you want to use. So a polynomial in x is an expression of the form an x raised to power n. We've seen this before in short. So with a0, a1 up to an, all real coefficients, right? Then n is a non-negative integer. We've said that already, that the power has to be non-negative whole number, right? So each exponent of x is a non-negative integer. We've said that also. Now, by that token, it means that the following things are not allowed in polynomial. Talking about the variable, so you don't have negative powers like x raised to power minus 1. So because the power has to be whole number, and you don't have fractional powers like x raised to power like half. Like you don't have any term like x raised to power half, or radicals like root x. Of course, root x is x raised to power half. So once you have any of these terms, it's no longer a polynomial. Then variables in denominations like 1 over x or x plus 5 over x. So something like this, except if you have maybe x squared plus 5x over x, and you know that by the time you divide through by x, you can have x squared over x, which is x, plus 5 over x, 5x over x, which is 5. So in that case, you can still say that's a polynomial. But if it is like this, you have x over x, 1, 5 over x is 5x raised by minus 1. So minus 1 at the power level means it's no longer a polynomial. Then when you have x inside functions like sine x, ln x, or absolute value of x, then you no longer have a polynomial, right? So let's talk about degree of a term, and degree of a polynomial. For instance, we already know what terms are, right? So when we talk about degree of terms, so for a non-zero term of the form ax raised to power n, the degree of the term is the exponent n, right? So for 3x raised to power 4, so this term 3x raised to power 4 has degree 4 because that's the power of the variable, right? The minus 2x is the same thing as minus 2x raised to power 1, right? So that means that the degree of this term is 1 since x is equal to x raised to power 1, and 7 has degree 0. So remember that for every constant is like multiplied by x raised to power 0, or the variable raised to power 0. So in that case, the degree of this term is 0. So that's talking about the degree of terms. How about the degree of polynomials themselves? So the degree of a polynomial in simple terms is the degree of a polynomial is the largest exponent of the variable in any term after like terms are combined. So if you still have maybe other x raised to power 4, other x, or other constants, you group them together, all right? And once you group them together, then so once you now have unique exponents, then the biggest exponent will automatically be the degree of the polynomial. So for 3x raised to the power 4 minus 2x plus 7. So this has degrees. So the first term, the first term has degree 4, the second term has degree 1, the third term has degree 0. But so the degree of the polynomial will be the biggest of the degrees, which is 4. So this is a polynomial of degree 4 because the variable, the biggest exponent, the largest exponent of the variable is 4, basically. So the zero polynomial 0 is a special case. In basic algebra, we usually say it has no degree. So 7, for instance, has no degree, So it has 0 degree, no degree. Now, let's talk about some special names for low degrees of polynomials. So they have special names. So talking about low degrees now, polynomials are often named by their degree. So a polynomial of degree 0, meaning that that's simply a constant, maybe just a number like 7 or minus 3 or 1 over 2. So it's a constant polynomial. So the degree is 0. So a polynomial of degree 1 is said to be linear because you have something like, so the highest power of x is 1, all right? So 2x plus 5 is a linear, is of degree 1. So we say it is linear because that's 2x raised to the power 1 plus 5, right? Then for degree 2, now we say that is quadratic because the highest power of the variable is 2. So you have x squared minus 4x plus 3. So the highest power of the variable is 2. No matter, the coefficient doesn't matter, just the power. So x raised to the power 2, that simply means this is quadratic. Then degree 3 is cubic. So when you have x cubed plus 2, for instance, all right, as far as the highest power of x is 3, then you say the degree, you say it's of degree 3 and the polynomial is a cubic polynomial. And then for degree 4, you have a quartic polynomial where you have the highest power of the variable as 4, right? So that's 5x raised to the power 4 minus x plus 1. And for degree 5, you also have quintic polynomials, which have the highest degree to be 5. So x raised to the power 5 minus 3x squared is a very good example of a quintic polynomial. And then you can also have degree n polynomials. That's nth degree polynomial, all right? So with that out of the way, let's talk about leading term and leading coefficient. Leading term and leading coefficient. So to talk about the leading term, first write the polynomial in descending powers of x. So that means that for any polynomial you have, it must start with the highest power. So you have a n x raised to the power n. So the next power should be less than that, no matter what. So the perfect way to write polynomials is to start with the highest power and go till you get to the constant, like we've been showing all along. So the leading term here is a n x raised to the power n. That is the leading term. That is once before you can't. If I write I think I need to give an example here to be very clear. So if I write if I just have, maybe I have 2x squared plus 5x and a 7x cube plus 2. You can't just take this as the leading term. This is not the leading term. Before you can talk about leading term, you have to rewrite in the standard form where the highest power comes first, followed by the next power, that's 2x squared, followed by the next power, that's 5x, followed by the constant. And then this is now the leading term, okay? So that's the idea of leading term. So first of all, write in standard form with the highest power coming first, and then others follow. And that first thing becomes your leading term. So the leading term is a n x raised to the power n, and the term with the highest, that's the term with the highest exponent. And then the leading coefficient is a n. So that's the coefficient of the leading term. So the leading term is the term with the highest exponent after you have expressed your polynomial in standard form, whereas the leading exponent is the leading coefficient rather is the coefficient of the leading term. So if I come back here from this example I gave, so so we say leading term is minus 7x cubed, then leading coefficient is equal to minus 7. Okay, that's the idea of leading term and leading coefficient. Now, it's important to pay attention to all of this because we're going to need those concepts as we progress. So, for example, for 3x raised to the power 4 minus 2x plus 7, the leading term is 3x raised to the power 4. And the coefficient of that, of the variable there is 3. So the leading coefficient is simply 3. Okay. So, and then let's go ahead and talk about standard form. Of course, I've talked about it previously. So standard form versus other or descriptive forms. So the standard form, a polynomial is in standard form if all like terms are combined. So it means that you don't have x raised to power 4 in many places. You have combined everything together. You don't have any, if you have constants, all these constants have been aggregated, they have been added or subtracted, or they have been made one. If you have different values of with different terms in x, you have combined all of them together. And finally, so all the terms are combined, like we said, and terms are arranged in ascending order of exponents. That is when you say that the polynomial is in standard form. So for instance, 3x raised to power 4 minus 2x plus 7 is in standard form, whereas 7 minus 2x plus 3x raised to power 4 is still the same polynomial, but it is not written in standard form. All right. So that's important. So we have other useful forms which can be said to be descriptive forms, right? So for instance, the same polynomial can appear in different forms that highlight different properties. So you can have it in factored forms. Now, factored forms are very useful when we are solving equations, or maybe you want to cancel, you're trying to evaluate the expression. All right. So you have factored form which shows zeros and roots. So it's easy to find the zeros of the expression in this way. So you have x raised to power 4 minus 5x plus 6, which is the same thing as x minus 2 multiplied by x minus 3. That's the factored form. Then you also have the vertex form for quadratics, which show the vertex. So like you have x squared minus 4x plus 1. So you can have, more like you're trying to complete the square that this is. So you have x squared minus 4x plus 4. So as you make it plus 4 like that, so x squared minus 4x, to complete that square, you have minus, that's plus 4 minus 4, right? So x minus 2 squared takes care of that plus 4, but then the minus 4 plus 1 gives you the minus 3. So that way, if you want to have something in vertex form, it's also useful in some situation. So you need vertex form for quadratics, or to show the vertex of, so the vertex simply means where this is a quadratic expression, for instance. So it is a parabola. So so it means that this expression cuts through the y-axis at 2, at 2, maybe not at the origin, but it cuts at 2 or so, or something like that. So all these forms, okay, I mean, we can even visualize that, right? X squared minus 4x plus 1. In that case, we know Desmos is very useful. Okay, Desmos is good for visualizing stuff. All right, so I go for Desmos now. Desmos, this is quite a bit. X squared plus 4x, x squared minus 4x plus 1, x squared, all right, minus 4x plus 1. So you see, yeah, so it means that the vertex is at 2, as you can see. So this vertex right here, it passes through, so part of its coordinate is 2, all right, and then you have the minus 3. So you see that the minus 3 that is standing out here tells you about the vertex. So that's 2, 3, like that. Or is it 2? I think it's 2 comma minus 3. Yeah, this is 2 comma minus 3. Yeah. So you take this 2 here and then the minus 3. So all these forms represent the same underlying polynomial, just described differently. Basically, that's what that is about. Okay. So we have polynomial functions versus polynomial equations. I think I've talked about this before, that when you just have the expression, it's just it's just the function. But by the time you equate it to something, it becomes an equation, like I said previously. So polynomial functions versus polynomial equations. A polynomial function is a function whose rule is given by a polynomial, right? Example, f of x is 3x raised to power 4 minus 2x plus 7. So this is a quartic polynomial function. Quartic because it is of degree 4. So, and it's a polynomial because it meets all the conditions. All the powers are whole numbers, no fraction, and all the coefficients are real numbers. So it meets the condition. So it's a polynomial established. It is quartic because it is of degree 4, all right? And then it's a function because the function is described by a polynomial. So this is a quartic polynomial function, and the domain is in real numbers, and all real numbers are, right? So it has the domain in all real numbers are. So then you have polynomial equation. So a polynomial equation sets a polynomial expression equal to something, often 0. So examples, this is a polynomial function. It becomes an equation once you now say that expression is equal to 0, or it is equal to whatever. All right. Maybe you can also say 3x raised to power 4 minus 2x plus 7 is equal to maybe 5x plus 2. That's still a polynomial equation. Then if you have x squared plus x minus 6 equals 10, is also a polynomial equation. It can be rewritten as x squared. So if you have something like this now, you can then say x squared plus x minus 6 minus 10, that's minus 16 equals 0. So this is also a polynomial equation. So as far as you equate the polynomial function to something, then it becomes a polynomial equation. All right. So when the expression stands on its own, you say it is an algebraic expression. But when you now say maybe f of x is equal to something, then it becomes a polynomial function. And then if you equate it to something, then you say to a number or to another expression, it becomes a polynomial equation. So the key ideas you need to pay attention to here is that a polynomial is simply an expression. All right. Then a polynomial function is a rule, because a function is a rule that assigns a dependent variable x to an independent variable f of x or y, if you like. So a polynomial function is a rule which maps x to f of x defined by a polynomial, right? Because of course x can be mapped to f of x, and maybe it is sine x, and sine x, of course, is transcendental. I think if you care to know, the opposite of polynomial would be transcendental functions. So you have polynomial functions. So those ones that meet all the criteria of polynomials versus transcendental functions. So transcendental functions, transcendental functions. So transcendental functions are simply functions that cannot be that are not polynomials. Of course, you can approximate them using polynomial, but they are not, in essence, they are not polynomials. So things like sine x, log x, cos x, all these kind of things, they are transcendental. Okay. So a polynomial equation is a statement involving equality, often solved for x. So once you now if you now equate a polynomial if a polynomial expression to zero, then or to any other expression, then it becomes a polynomial equation, and that is the essence of this playlist, by the way. So identifying degree and structure of 3x squared minus 2x plus 7, right? I think we've talked about this. Maybe this is just like some kind of repetition. So consider the polynomial 3x raised to power 4 minus 2x plus 7. So it has three terms, 3x raised to power 4 minus 2x plus 7. Don't forget, you take each term with its sign so that you don't get confused. Take each one with its sign. So you have 3x raised to power 4, which is like plus 3x raised to power 4. Then minus 2x, you pick that. Then 7, that's plus 7. So you can write that as 7 instead of just writing the plus in front of it. Then you have the coefficients. The coefficients are 3, minus 2, and 7. All right. And then the degrees of each term. So for the first term, the degree is 4. The second term, the degree is 1. For the last term, which is constant, for every constant, the degree is always 0. Then we can then talk about the degrees of the polynomial. So the degree of the terms is for each term, but the degree of the polynomial is the highest exponent, which is 4 here. So the degree of the polynomial is the degree of the highest term of the polynomial. So highest exponent is 4. So the polynomial is of degree 4. And we say this is a quartic polynomial, right? And then if you since this is already expressed in standard form, the leading term is 3x raised to the power 4, while the leading coefficient is the coefficient of the leading term, which is 3, right? So we have all of those ideas. Then as a polynomial function now, we can then say, so as a polynomial function, we can say that f of x is equal to 3. So when you write it just like this, 3x raised to the power 4 minus 2x plus 7, it is just like an algebraic expression or just a polynomial. But it becomes a polynomial function once you now write it like this. So you have f of x equals 3x raised to the power 4 minus 2x plus 7. Then this is a quartic polynomial function. Then if you now say f of x, which is 3x raised to the power 4 minus 2x plus 7 equals 5 or 0 or anything, then it becomes a polynomial equation, right? So we go to this next part. So non-example. So why, for instance, is x plus 5 over x not a polynomial, right? So consider the expression x plus 5 over 4. X plus 5 over x. So if you break it apart, I expressed this before. So you have x plus 5 over x. That means you can break it up as x over x plus 5 over x. X over x is 1. 5 over x is the same thing as 5x raised to the power minus 1. So this minus 1 is negative. And for a polynomial, the power has got to be non-negative. And it has to be a whole number too. So this is non-negative. So that breaks the rule. So the term 5x raised to the power minus 1 has exponent minus 1, which is negative. This violates the polynomial requirement that exponent must be non-negative integers. Therefore, x plus 5 over x is not a polynomial in x. So we can have important contrast to that, like x plus 5 is definitely a polynomial. So it is linear and it is of degree 1. But x plus 5 over x is not a polynomial because it introduces the term x raised to the power minus 1 by the time you divide through by x. Okay, so let's do some quick checklists before we see practice questions as we bring this to a close. So quick checklist: is this a polynomial in x? Now, to decide if an expression is a polynomial in X, check the exponents of X. Are all exponents whole numbers like 0, 1, 2, 3? Of course, 0 is allowed. And so all exponents must be whole numbers with at least 0, then 1, 2, 3, 4, 5, 6, positive. Then if you see any exponent like -1, 1 over 2 root X, etc., then that is not a polynomial automatically. That's talking about exponents. Then position of X. X must not appear in denominators. If X appears in denominators at all, it means that then the best is by the time you divide through, the X disappears from the denominator. But as far as after dividing, you still have X at the denominator, then that is not a polynomial. So no 1 over X or things like X plus 5 over X. Okay. Of course, if you have X squared plus 5X over X, that will still be a polynomial, right? Because X would have disappeared from the denominator. Then X must not appear inside radicals, absolute values, strict functions, logs, etc. So no square root of X, absolute value of X, sin X, ln X, or arctan X or something like that. All of those are not allowed. So they automatically not put. So the expression will automatically not be polynomial if that happens. Then talking about the coefficients can be any real numbers, including fractions or irrationals. So the coefficients of a polynomial can be fraction, it can be irrational, but it must not be complex. That's all. So it has to be real. So these are the conditions, three basic conditions for a polynomial. You have the coefficients are all real numbers, and then the exponents, the powers, are non-negative integers. That mean integer meaning that they are whole numbers and they are always positive. So if any of the rules break, if any of these three breaks down, then you no longer have a polynomial. So if all exponents are non-negative integers, right, X doesn't appear in forbidden places. The expression is a polynomial and its degree is the largest exponent on X. So if all exponents, right, are non-negative integers and X doesn't appear in forbidden places, like X doesn't appear like 1 over X and all that, the expression can then be said to be a polynomial, right? And its degree is the largest exponent on X. So for summary sake, I can say conditions for something to be conditions for polynomial, if you like, conditions for polynomial by way of driving home the point. Like I've said it plenty times. So first of all, exponents for exponents now, they are integers, meaning that no fraction or anything, and then they are positive, basically. So the exponents are integers and they are positive. So integers meaning they are always whole numbers, and positive they are always non-negative. Number two, for coefficients now, the coefficients are always real. That's all. So we 1, 2, 3 conditions. Once those three conditions are met, you have a polynomial right there. Okay, so these are some practice questions. I'll just flash through one after the other. So for this first set now, for each expression, decide whether it is a polynomial in X. If it is a polynomial, state its degree, leading term, and leading coefficient. If it is not, explain why. For instance, this first one is a polynomial for sure. I mean, we worked with it all through. So this is a polynomial. The degree of the polynomial is 4 because that's the power of the highest coefficient that's the highest exponent, so to speak. Then the leading term is 3x raised to power 4, and the leading coefficient is 3. Then the second one, this is also a polynomial. Don't let 1 over 2 confuse you. So 1 over 2, 2 here is not x. So fractional coefficients are allowed as far as they are real. Okay. So in this case now, the degree is 3 and the leading term is 5x cubed. The leading coefficient is 5. Now, C, of course, is not a polynomial because by the time you divide through, x cancels x, you have 1. 5 over x leads to 5x raised to power minus 1. So this is not a polynomial because it introduces 5x raised to power minus 1 there. Then D is not a polynomial too because the power of, for the first time, the power of x is 3 over 2, which is not an integer. It has to be whole number, integer, right? The last one is a polynomial, of course, and the degree is 5. It is a quintic polynomial, and the leading term is minus 7x raised to power 5, and the leading coefficient is minus 7, okay? So then you have other questions like classify each polynomial as constant, linear, quadratic, cubic, quartic, or quintic. Okay, this is easy. This is just linear. Okay, sorry. This is constant. This is a constant polynomial. This is linear. This is quadratic. This is cubic, and this is quartic. We don't have a quintic one here. This E here is quintic, like I said. Then question 3, write each polynomial in standard form and then identify the leading term and coefficient. Of course, if you want to rewrite this, 3x raised power 4 has to come first, minus x squared plus 7, and then the leading term is 3x raised power 4. So you can do all of that. For each polynomial, find the degree and list all its terms with their coefficients and degrees. I mean, we saw that previously. You want to try your hands on that. So 5, decide whether each expression represents a polynomial function in X. If yes, write the degree. If not, explain. Of course, A is not a polynomial because you have X under, and there's no way that X is going to cancel out. G of X, of course, is a polynomial. All right. The degree is 3. Then h of x is not a polynomial because this is root x means x raised power half, right? And in that case, the power is not an integer, so it is not a polynomial. Then k of x is a polynomial. The degree is 4. It's a quintic polynomial. Then question 6, construct a polynomial in standard form that satisfies each description. A quadratic polynomial with leading coefficient 2 and constant term minus 3. So you see, this is a quadratic polynomial with leading coefficient 2. So that means you are going to have 2x squared, at least 2x squared minus 3. Any other thing can come in between. We don't care, right? As far as these two conditions are met. So it's a quadratic equation. That means the highest power of x is 2. So, and the leading coefficient is 2. That means this 2 is attached to the x squared. So you have 2x squared and the constant term is 3. So at least you can have 2x squared minus 3. You can have 2x squared plus 4x minus 3. So whatever comes in between doesn't matter as far as you meet this other condition. So a cubic polynomial with leading coefficient minus 1, that's minus 1x cubed and no constant term. So maybe you just have minus 1x cubed plus 5x squared plus 7x, no constant. A quadratic polynomial with degree 4, leading coefficient 5, that's 5x raised power 4, and exactly 3 times. So 5x raised power 4 plus 7x minus 7, or any other thing you do after that, as far as the highest power is 5 and the degree, as far as the highest, the coefficient is 5 and the highest power is 4, any other 2 times you add doesn't matter. But no, you shouldn't add any other term that is higher than 5 than this 4. That has exponents higher than 4 for sure. Then explain in the sentence or 2 why each of the following is not a polynomial. Of course, this is not a polynomial because the power of x here is minus 2. So the power of a polynomial, the exponent has to be non-negative and it has to be a whole number. So this one disobeys the law of it being non-negative because this is actually negative. And this is not a polynomial because you have x in the wrong place, like we said earlier. C is also not a polynomial because this would have made it a polynomial, but this one destroys the idea because this is x raised power half right here, and you cannot have a fraction as power in a polynomial. Then number 8, the polynomial p of x equals 4x raised power 5 minus 3x plus 2x minus x plus 7 is given. What is the degree of p of x? Clearly, that's 5. That's the highest power. What is the leading term? That's 4x raised power 5. What is the leading coefficient? That's 4. Is p of x a polynomial function? Explain briefly. Of course, it's a polynomial function. Yeah, because it doesn't, all the coefficients are real. All the powers are non-negative integers, right? Even when you have 7, it's 7x raised power 0. 0 is non-negative and it's an integer. Okay. Question 9, write each description as an explicit polynomial in X. A linear polynomial with slope minus 4 and y-intercept 6. So, we've done things like this before. So you want to try your hands on that. For each polynomial, decide if it is already in standard form. This one is not in standard form because the highest power should come. It should come in order of the value of the exponent. And this is also... Well, with the biggest exponent first, that's all. So this is not in standard form, this is not in standard form. None of them is in standard form. Okay. So, and then you can write in standard form, that's x raised power 4 minus 2x squared plus 3. And for this to be x cubed plus 6x minus 5. For this to be 4x cubed minus x squared plus 7x minus 1. So that'll be standard form. So with this, we come to the end of this interesting video, introducing us to the concept of polynomials and of course polynomial equations in general. Okay. Thank you so much for listening to this. Let me know how helpful this is for you. And if there's something else you'd like to learn as far as this playlist is concerned, feel free to let me know in the comment section either on Facebook or on YouTube. Okay. If you have subscribed already, I thank you very much. If you have not, of course, you don't want to miss out on any other thing on this channel. So why not go ahead and subscribe right now, hit the notification bell so you can always get alerted each time a new video is released. Okay, you can take it a step further, become a member of the channel by clicking on join, and it gives you some special privileges like having a one-on-one chat with me, physically or online, depending on your level of membership. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.